Today on Science Max, we're looking at
Chemicals!
Chemicals make up everything around us, and we're finding out which ones you can mix together to make spectacular science.
Whoa!
Woo! Cutest science ever. Today on Science Max, Experiments at Large. Greetings, Science Maximites! My name is Phil McCordick, and the name of the show is Science Max, Experiments at Large. Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be Science Maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. And that's what we're gonna be looking at today, chemistry in all its forms. And of course, because it is Science Max, Experiments at Large, we're going to max out the vinegar and baking soda volcano. So I'm off to the Center for Skills Development and Training. Come on. Hey, Talina.
Hi, Phil.
How you doing?
Good, how are you?
Good. This is Talina. She's going for her PhD in chemistry from McMaster, right?
Yep.
Awesome, which means you can help me max out the baking soda and vinegar. We need vinegar. You grab that vinegar. And vinegar volcano. So what happens when we mix these two chemicals?
Well, vinegar is an acid and baking soda is a base, and when you mix them, they neutralize each other to produce carbon dioxide and water as a byproduct.
So acids and bases are kind of like opposites.
Yep.
So I guess that makes sense. When you put them together, crazy stuff happens.
Yeah.
Awesome, chemistry. Okay, so I want to use this much vinegar and this much baking soda.
What's with the fish tank?
The fish tank is where I want to mix it all together. What do you think?
Awesome.
Maxed out. Okay, let's move the fish tank somewhere where we won't make a huge mess. It's a little heavy with all that. We gotta. No, we're gonna have to take a couple trips. That's kind of heavy. Okay, so we'll take this and that, and then this, and that. No, hold on. I can do it. Just one more. Okay, good. Okay, good. Yeah. I took too much. Uh-oh.
That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes. But if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on, made of chemicals. My lunch, chemicals. Roller skate, chemicals. My jacket, chemicals. This guitar, chemicals. My shoe, chemicals. This watch, chemicals. This fish, Chemicals. 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 Me. Chemicals. You. Chemicals. Ramona. Chemicals. No, I said you chemicals. Never mind. This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter. Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got 1 oxygen, 2 hydrogen, bam, you got a water molecule. 1 carbon, 2 oxygen, hey, it's carbon dioxide. 2 carbon, 2 oxygen, 4 hydrogen, skadoosh, vinegar. 1 sodium, 1 chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar.
Let's take a closer look at what's going on when we mix vinegar and baking soda. All chemicals are made of atoms. There's only 4 types in our reaction: carbon, oxygen, hydrogen, and sodium. When they go together like this is a molecule of vinegar, or acetic acid. And this is a molecule of baking soda, or sodium bicarbonate. When chemicals react, they switch atoms. That one goes there, this one goes over here, and then this one turns into this, and then what you end up with are new molecules. This one is called sodium acetate, and this one is carbon dioxide gas, the gas you breathe out. And do you recognize this one? Right, water, H2O. Why all this happens gets complicated, but the study of chemistry is all about how molecules are built and react with other molecules.
All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our 3rd bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it.
Our vinegar and baking soda reaction went pretty well. But now we're gonna try it with a much stronger type of the same kind of acid you find in vinegar.
Carefully putting this down. And watch out for the baking soda. You never know when it'll get out. And, well, I guess that's just baking soda, huh?
Yeah, that's pretty safe.
Yeah, okay, good. So this is baking soda vinegar volcano version 2. We have this differently shaped glass. What do you call this again?
That's an Erlenmeyer flask.
Why is it called that?
It's actually named after a scientist.
Did he look like that? Was he sort of shaped like this?
No.
No? Was he just a good chemist?
Good scientist, and I think he designed the glass.
Oh, see, there you go. So if you want to have a glass named after you, be a good chemist and design a glass. I want to make a fill beaker. So this is 100% acetic acid.
Yep.
And what's the difference between this and vinegar?
Vinegar has 5% of this and 95% water. But this is 100%, so it's much stronger.
Much stronger. Can you put this on your French fries?
No, I wouldn't be putting it on your French fries.
No? As chemicals go, how dangerous is this?
It's not too dangerous, but you definitely don't want to be breathing it in, and you don't want to be eating it.
Or getting it on your skin. That's why I'm wearing these fancy pantsy gloves. So what I'm gonna do is I'm gonna pour the acetic acid in this, what's this called?
That is a graduated cylinder.
Because it finished school. So it graduated. Now you're gonna mix water and food coloring and soap all together.
Yep.
And pour it into there?
It'll help dissolve some of the baking soda, so hopefully it'll react better with the acid.
Sounds good. Face protection.
Oh.
All right, that's good. And now, when we do it, I want to add the funnel at the end to like accentuate the concentration of, but I don't know if it's gonna go so fast that I won't be able to get it in there, but we'll try it.
Try it.
Vinegar, baking soda, volcano, version 2. Woo!
Good thing you got the mask.
It smells a lot like vinegar. It's really strong. Oh. That was pretty good. But what can we do to make it even bigger?
Well, you could try using a different chemical reaction.
Ooh, okay. Like what?
The decomposition of hydrogen peroxide produces oxygen gas, and so that one's pretty vigorous if you use a catalyst.
So we want something that makes a lot of gas so that it makes a lot of bubbles when you put the soap in it.
Yep.
Great, let's do it. And the sooner we leave that smell, the better, I think, for my taste. Today we're combining two different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. Very cool and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous. So,
So, what happens if we combine these two deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land? No, we create salt. Good old normal table salt. These two substances combine to make NaCl, salt. Something completely and totally safe. Chemistry.
We've gone from vinegar and baking soda to 100% acetic acid in baking soda, and now we're doing the...
Vinegar and baking soda volcano version 3. No longer vinegar and baking soda.
Nope.
What are we using this time?
So here we have some hydrogen peroxide.
Oh, that's the stuff you use at home to put on a cut, right?
Yeah, but the stuff at home is only 3%. This one's 30.
So much, much stronger.
Much-
10 times stronger.
Yes.
And is this more dangerous?
It's definitely corrosive, so wear your gloves.
Corrosive means it could eat your skin,
It can burn your skin a little
which
bit.
is why we are wearing gloves and blast shields. What's gonna mix with this?
So here we have some potassium iodide, which is a salt, and it's mixed in with some water.
The most important part of this reaction is the fact that it creates gas.
Oxygen
which
gas?
makes bubbles when you put in dish soap, right?
Yep.
So one big squirt of dish soap like that. Mix it up. Now we go over to the blast zone.
That's plenty.
All right. Now that's a reaction. Looks like there's steam coming off here. Why is that happening?
Well, it is an exothermic reaction, so heat is being generated as the reaction proceeds.
Oh, cool. Can we lift our visors now?
Yep.
Awesome. And what's being released? What's the gas that's coming off here?
So it's oxygen gas that's being produced.
Oxygen. What we want to do is make this even bigger, but first, can we do it again?
Sure.
Because I have an idea. Hold on. I think we should repurpose our old volcano. What do you think?
Sounds like a good idea.
Okay, so if we put it over here. All right, volcano version 3.5. Hydrogen peroxide, potassium iodide. Right, here we go. Whoa!
Looks like lava.
Whoa! Look at that. Now that is a big volcano eruption.
Just covered the town.
That is completely, yes. That town is gonna be very clean because it's all soap bubbles. It's the cleanest volcano this side of Science Maxville. So I still think we can do this bigger, though, right?
I agree.
Oh, I know. What if we use some sort of a tube, like maybe one of these, right? And then we attach it to like an air compressor.
I think you'd get some height.
Yeah, and we go outside.
The atom in 60 seconds.
The atom is the smallest unit in a chemical element. Atoms are made of 3 parts. Part number 1 are these guys, protons. They have a positive charge. The number of protons determines the element. 1 is hydrogen, 2 is helium, 3 is lithium, and so on. The protons sit in the middle here, which is called the nucleus. They sit in here with part number 2, these guys. They're neutrons and they have a neutral charge. Now I've got 8 protons and 8 neutrons in this nucleus, making this an atom of oxygen. Orbiting around the nucleus are these tiny guys. They're electrons and they have a negative charge. I will demonstrate using kittens.
Kittens are perfect because just like electrons, kittens are really small. And just like electrons, kittens move around randomly. You never know where they're going to be, but an oxygen atom should have 8 kittens, or electrons, somewhere inside. These kittens are constantly escaping, but guess what? That happens with electrons too.
There you go, the atom, a nucleus of protons and neutrons surrounded by randomly moving electrons. Cutest science ever. How do you guys feel? Did you learn something? Huh? Pause up. Who learned something?
Talina and I have made a bunch of chemical reactions, but in our quest to max things out, we've got a new plan. Hydrogen peroxide and potassium iodide create gas. One way to max out the reaction is to contain the gas in something like a tube. We're gonna put the hydrogen peroxide in the tube first. Then we're gonna put in the potassium iodide in the top through a one-way valve. Then we're gonna pressurize the container. When it finally reacts, it will shoot up through the valve and we'll see how high we can get our stream of bubbles to go. But be warned, capping anything and not letting it escape is never a good idea. So we've got a release valve to make sure things work out. This is one of those experiments that's definitely on the list of don't try this at home.
Vinegar baking soda volcano version 4, hydrogen peroxide, potassium iodide. And what we're gonna do this time is we're gonna put it in this tube. Hydrogen peroxide goes in here. And we've got, Talina, do you have the potassium iodide in syringes?
Yeah, 2 syringes full.
2 syringes full. About there is good. And then soap. Good amount of soap in there. And so what we're gonna do is we're gonna close this off and tighten it up. And then we're gonna pressurize the whole system. And then we're gonna add the potassium iodide. And it's going to be spectacular, we hope. Okay, that's on tight. This is all good. Putting this down here. And potassium iodide goes in here.
Ready?
Puts down. Ready? 1, 2, 3, go. And we back away slowly. Whoa! Whoa! Yeah, that's what I'm talking about. Okay, let's check it out. Woo! All right, there you go. Vinegar and baking soda volcano maxed out. Thank you, Talita. That was great. If you guys want any instructions for the stuff that we've done today, they're all on the website. And thank you very much for watching Science Max Experiments at Large. We kind of need to clean up a lot, don't we?
Yeah.
We have out here, we have the other room. So tell you what, you get a mop, I will get the hose and a wheelbarrow for the sud.
This episode is all about chemical reactions.
Nom nom nom, nom nom nom, nom nom nom, delicious.
Reactions to make things fly, to make things glow, to make things pop, and to make things fly.
That worked.
Wait, did I mention the flying? I'm sure I did, but I'm mentioning it again because it's awesome. All on this episode of Science Max Experiments at Large.
Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away!
Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. Come on, let's max it out. So first, I need an expert to help me. Lisa from Logix Academy, of course. Logix Academy people have helped me launch all the rockets on Science Max. This is gonna be great. I'm gonna get my helmet first. Okay, let's launch some rockets! Let's go!
Whoa, wow, it's really dark in this room. I can't see anything.
Bill?
Lisa?
Bill?
Lisa?
Bill?
Where did this come from? I guess the portal's malfunctioning. Hey, Lisa!
Hi!
From Logix Academy, great to have you here.
Great to be here.
Just put this over there. We are here to max out the chemistry rocket!
Ooh, what is that?
It's just a small plastic container. But when we put an antacid tablet in there and some water,
We get a chemical reaction.
we get a chemical reaction. And so that's what creates the pressure. And then that pops the lid off and we get a little rocket.
Kaboom!
But now we're going to max it out. Get a bigger container and more.
Wait.
What?
How about if we launch a whole bunch of them?
Ooh, so we just get a lot of the small one and we launch them all at the same time.
Exactly.
Okay, great. So we just need a whole bunch of these and a whole bunch of.
And a whole bunch of science antacid.
Yeah, well, that's okay. I get them both in bulk. Come on, let's go put it together. I And I'm a base. And we are enemies. Whoa.
Well, we're not really enemies.
Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons.
You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react.
Whoa. That is until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need it more. I want more. I want more protons. Here.
Water is a solvent, allowing the chemical reactions to take place.
Depending on the strength of the acids and bases, that reaction can be mild. Would you like a proton?
Oh, no, really, I could.
Please take it.
Oh, well, thank you, that's very generous.
Have another.
No, perhaps, maybe I will.
Here's
Yes,
one.
Okay, maybe just one.
But if the acids and bases are strong, the chemical reaction can be really extreme.
This is what's going on in the antacid tablet, and why, without water,
Nothing happens. Oh, water! Water! Come on!
What'd you do?
What?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket not by making it bigger, but by making more of them. How many more?
400 caps all glued down, 400 antacid tablets, or part of,
Yep.
all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down.
We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on.
Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flip the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah. It's good luck if you catch them.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go and we'll clean this
All
up
right.
afterwards.
Yeah,
okay.
let's do it.
Okay, let it go. Whoa. Whoa. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it, that separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready?
go! Science!
Our first attempt to max out our chemical rocket was 400 plastic containers.
Oh, yeah.
That worked well, but now it's time to make the container larger.
Whoa! Giant maxed out chemistry rocket canister. I have a big plastic container with a groovy lid that sits there on airtight, which is great.
And I have a giant jar of antacid.
How many? It was like 60 antacid tablets or something?
At least.
This works exactly the same as our smaller containers. We dump the antacid in, seal the lid airtight, then flip it over. And now would be a good time to mention not to try this at home.
Okay. Oh, it's not gonna take long. All right, so that was the canister version. Now we need the pop bottle version, the
Yes.
rocket version.
Yes.
Okay, let's go make that.
Let's do it.
Okay. This is a light stick.
It creates light using a chemical reaction. There's a liquid chemical inside and also a glass container that holds another chemical. When you bend a light stick, you break open the container and the two chemicals mix, creating light.
There you go. Light sticks. Chemical reaction. And yes, of course, we're gonna max it out. This is a whole bunch of the two chemicals in a light stick. Let's max it out.
So how does a chemical reaction produce light? Well, a lot of chemical reactions produce energy. You might think of a chemical reaction producing heat. Well, heat is a kind of energy. This chemical reaction also produces energy, just energy in the form of light. It's just a different kind of energy.
Whoa, maxed out light stick!
And now for a Science Max quiz. Chemical change or not? What's a chemical change? Well, let's demonstrate. Look at this. It's a happy little molecule of iron. And here's another molecule of oxygen. If they were to have a chemical change, they would react and form different molecules. Look, it's a molecule of rust. Rust is a different chemical than either iron or oxygen. It's a chemical change. Now, if these molecules mixed and did not change, then it's not a chemical change, it's a physical change. Sometimes it's hard to tell if it's a chemical change just by looking, but asking what kind of change it is leads to good science. So let's look at some examples. Vinegar and baking soda. Is it a chemical change? Yes. Vinegar and baking soda react to form different chemicals. Sodium acetate, that's the white stuff that's left over, and carbon dioxide, which makes the bubbles. How about a nucleation fountain with Diet Cola and mints? Haha! A lot of people think that's a chemical change, but it's not. The mints cause carbonation, the bubbles, to escape faster. But in the end, you still have cola and mints, no new chemicals. And without the carbonation, nothing happens. So, it's a physical change. Take a guess at this one. Glow stick chemicals. Well, producing light or heat is usually a sign of a chemical change. How about mixing sugar and water to make a sugar pop? That's a physical change. You start with sugar and water, you mix them, and when you have a sugar pop, what chemicals are you left with? Well, sugar and water. So, no chemical change. It can be hard to tell sometimes, but whenever two things mix, think to yourself if it's a chemical change or a physical change. And now you know it's either one or the other. And that's the first step to good science. Thanks for playing our Science Max quiz. Our maxed out rocket worked great. Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right?
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah.
And so the magnet sticks to the paper clip.
And so that's what we have here. You see, the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic. So we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher like so.
All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go.
And then, as we pull the bottle over, we bring the bag up this side, and there, the water and the antacid have never touched.
No reaction.
All you need to do now is just, we pull this magnet away, and the bag will fall into the water, and then we will have the launcher down here, and we pull the release, and the rocket will go.
We add some weight to the launcher to help keep it in place.
Okay, right, wait, glasses.
Safety first.
Okay, ready?
And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
3,
2, 1.
1, launch! Woo! That worked.
Yeah, I hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of 3, 2, 1, go! There it is. Yeah!
We tried it outside and it worked great. The only thing left was to max it out even more.
So, larger chamber,
Yep, more antacid.
more antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together, and we can increase the size
All
of
right.
the chamber. This is sodium acetate. How do you get sodium acetate?
Well, when you do a vinegar and baking soda reaction, what you have left, once the reaction is finished, is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a supersaturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform.
Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this.
Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right before your eyes. Because we heated the water, it allowed more crystals to dissolve in it.
Ooh.
But then it cooled down afterward. There's more crystals sitting around in this water than there should be at this temperature. They want to turn back into crystals, and all they need is something to start them going.
I've colored this one green because, I don't know, science. Maybe it'll look cool.
A tiny crystal on the end of the stick is all we need to start the reaction happening.
Whoa! Wow. And there you go, sodium acetate. That one wasn't done yet.
We've gone from small containers
Oh, yeah.
to a large container to a rocket.
Yeah!
So what's next?
Super maxed out rocket!
12 2-liter bottles all spliced together to give us a very large chamber to build up pressure with.
So the chamber is all the same. So it's all one big hollow tube, and now we're gonna fire it off. Let's go!
Let's do it.
Awesome rocket! Yeah!
Lisa and I follow the same procedure as before. We use a bag of antacid tablets held up inside the rocket with a magnet. And once it's sealed on the launcher, we pull it off, let the antacid mix with the water, let the chemical reaction happen for a while to produce enough gas pressure, and then we fire it.
Okay, here we go. 3,
2, 1, go!
Oh my God!
That is the highest I think we've ever shot a rocket on Science Max.
That's amazing.
Well done. Chemical reaction rocket. Thank you very much for joining us on Science Max Experiments at Large. We should build another rocket because
I
that
think so.
one is probably broken.
That's done.
Okay, let's go.
Let's do it.
All right, so this time I think what we should need to do is... Oh no, it's nothing but garbage cans in there. We gotta turn the portal off. Come on, we gotta get...
Stable structures are what we're building on this episode. Bridges, cups, pencils, blocks, boxes. They're all being built up and falling down. Plus, how stable can you make a structure using fruit as the base? Stay tuned to find out on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Get your hard hats out because today we're gonna be building things. Like I always say, what's the point of science if you can't use it to build cool stuff? And today's episode is called Stable Structures. Now, stables are the buildings where horses sleep. So, stable structures means... I think I have the wrong kind of stable. Today, we are going to be building a gumdrop dome. And gumdrops are already kind of dome-shaped, but they don't hold a lot of weight. Yeah, can't hold much weight. But you can make it hold a lot of weight if you build a geodesic dome. A geodesic dome means a round shape made out of straight lines, and that's what I've made here. All I used is gumdrops and toothpicks. It's very easy to make, and I'll show you how to do it. First, you need to start with a pentagon, a 5-sided figure. 1, 2, 3, 4, 5. And then stick them all together, obviously, with toothpicks. Then what you want to do is you want to start making triangles. So you stick a toothpick in here and a toothpick in here, and then you put a gumdrop at the top of this triangle, just like this. And then you make another triangle here and here and here, and it becomes a whole bunch of triangles, you see? Easy to make as long as you start with a pentagon on the bottom. Now, once you've built one, I suggest you build 2 more, because then you will have a stable base and you can see just how much weight these hold. Yeah. You wanna max it out? Oh, okay. Let's max it out. Oh, a little collapsing, but still not bad for gumdrops, right? So there you go, the geodesic dome. That's what you research if you want to learn how to build one of these for yourself. But now, let's max this out even more. Okay, now I just need an expert to help me out. Do you like my new interface? It's good, right? Watch this. Oh, wait a minute. That's not, okay. Wait, no, that's not the right gesture for that. It's all gesture-based, so I gotta, this? Nope. This? Nope. That? Ooh, okay. Expert. I want experts. Oh, okay. It's voice activated. Great. Sarah from Mad Science. She'd be perfect for this. Good. Close. I can leave it running. Sarah?
Hey, Phil. Back here.
Hey, Sarah. Sarah from Mad Science. Great to see you.
Thank you. Great to be here. I like your lab coat. It's a really nice color.
Wait a minute. It's supposed to be yellow. It must have changed to orange in the portal. That's okay because this is not the first time that's happened, so I've installed a little secret thing on the app that allowed me to get a new one from storage.
Oh,
Watch
perfect.
this. Huh. Didn't work. Oh well, I'll get another one later. All right. Anyway, we are going to max out the geodesic dome.
Amazing. That's so cool.
Yeah, so we just want to make it bigger. So how do we do that?
Okay, well, there's a couple ways we could do that. We could add a few more points of connection, change the shape of it, make it a little more complex so it's a little bit bigger. Or we can use the design right now and use different materials to make it bigger.
Okay. Well, you know what? I think we should do
both of those things. I think we should make it more complex and bigger, but why don't we start with bigger? But we'll use the simple design right here, and we'll just get like long wooden poles instead of toothpicks.
Perfect, yeah. And then, what will we use for the gumdrop?
I guess we can't get big gumdrops, huh?
No, I don't think so.
What about oranges? Huh?
Yeah, oranges could work.
Maybe, yeah, because you could stick the poles in and then the oranges would be, okay.
Yeah, that's
We'll go to the Science Max Fruit Market and we'll get some oranges.
Perfect.
And I'll get a yellow lab coat. I don't know why that didn't work. Is this a maxed out number of oranges?
I think so.
Or is it just a mediumed out number? We don't really need many more oranges than this.
No.
So, there we go. So we got our oranges. Those are going to be our gumdrops, and
These wooden dowels will be our toothpicks.
we just have to start with a pentagon, right?
Yes.
5 sides. So why don't we just lay that out and see what it looks like here.
We start building this dome the same as the gumdrop dome.
So, like this.
We stick the dowels into the oranges to make our 5-sided pentagon.
Good, like that.
And then we go up from there by making a few triangles and sticking the oranges on the tops.
Oh.
But because the oranges are heavy, the triangles are pretty wobbly. That is, until we get them all connected with cross pieces.
Yeah.
After that, it seems to hold up pretty well.
Okay, let's see if it holds it up. Whoa! That's exciting. That is very exciting. Let's do the same thing. So you make a triangle here, I'll make a triangle there, and then we'll connect them.
Sounds good.
2 layers, orange dome. I'm pretty excited about this. This is nice.
I'm surprised that the oranges actually hold it together because
Oranges aren't really that strong.
No, exactly. But the structure itself is really strong based on the design of it.
Yeah, because it's all about the shapes, right?
Exactly. And we're using lots of triangles today, which are one of the strongest shapes on Earth.
Ooh, strong. Well, then making something out of a lot of triangles makes it really strong.
Exactly.
Yeah, okay, so let's make that top layer of
All right.
things. We only need 1 more orange.
Yeah.
This will be the one, top layer.
Right in the middle.
1 orange on top with 5 dowels from each point and
Yeah! Orange juice high five.
in fact, it worked so well, there's only one thing left to do.
Is there a way that we can maybe max it out even more?
Watermelon? Watermelon. We could get the round watermelons. You ever
Yeah.
seen those? They're like the size of a bowling ball or
Yeah.
smaller, a little bit smaller.
That's perfect. And they're nice and full inside, so they should be able to hold the posts into place.
Okay, we'll try it one more time with watermelon. Inside dome high five. Yeah! You may have heard of cup stacking, and if not, you're missing out because not only is it fun, but it's something that kids are the world record holders at. And it's all about, you guessed it, stacking cups. Now, I have learned the pattern, but I'm not super fast at it. The world record is actually 4 seconds, and this is what that looks like. But you can't use camera tricks to help you. You have to practice to get faster. Now, you don't need to use official sports stacking cups, but if you don't know your science, some things will work against you. First of all, these cups have holes in the bottom, which makes them not very good as, cups. Why do they have holes in the bottom? Because of science. You see, when you pull the cups apart, there is air that needs to get inside this cup. If you don't have a hole, like these ones, the air makes them stick together because there's nowhere for the air to get in except for underneath, and they will stick. Once again, let's compare. Also, you want the cups to have some weight because if they have some weight, they'll fall out of each other easily. If they don't have any weight, like, say, these styrofoam cups, it becomes very difficult. And cup stacking with trash cans. Okay, here we go.
Even though these trash cans were heavy, they didn't have holes in the bottom, which means they stuck together. A lot. So why didn't I drill holes in the bottom of these trash cans?
Okay, and then Well, I needed them in episode 6 to make 11 barrels of slime. Okay. 2. No. But I eventually did it. And time. Okay, there you go. The world record in trash can stacking. I know it doesn't seem very fast, but first of all, that was hard. And second of all, I am the only one to do it. So therefore, I hold the record. Sarah and I have already made a great dome out of oranges. Now we're maxing it out even more, but this time using
Watermelon!
watermelons! But not the giant watermelons,
Nope.
the perfect spherical watermelons. They'll have to do pretty good to be better than the oranges.
Definitely.
All right, so we just do it the same way?
Same way.
All right.
Let's do it.
I'm sure I'm not telling you something you don't know when I say watermelons aren't great for building structures with. Super wobbly. But the fact that we can make a structure using watermelons just proves how amazingly strong a geodesic dome really is. Have we done it?
Yeah.
We've done it! Yeah, watermelon dome!
All right, we've got our gumdrop dome,
We've got our orange dome!
and we've got our
watermelon dome! These are awesome maxed out domes. What do we want to do to max it out even further?
I think the watermelons were a little too heavy. Maybe we should go back to something lighter.
So we can make it out of gumdrops, which will be
Yeah.
like more complex.
Exactly.
And we won't get orange juice raining on our heads all day,
Yep.
which is what happens with this one.
Max Historica.
This is Leonardo da Vinci. Ciao. One of the greatest inventors to ever live. And this is a pile of wood. One of the greatest piles of wood to ever be piled. Now, Leonardo is going to construct a bridge out of this wood. This is Leonardo's hammer. One of the worst hammers in the history of hammers. Now Leonardo must construct his bridge using no tools at all. No, that hasn't been invented yet. How will Leonardo construct a bridge using no tools at all? Well, he is one of the greatest scientific minds. One of the greatest scientific minds in history. Oh, each piece of wood is supported by another. And that's what's known as Leonardo da Vinci's self-supporting bridge. Leonardo's done it. But there is a flaw in the bridge. It's very strong when you apply downward force, but not so strong when you push on it sideways. Fortunately, Leonardo can devote his great mind to figuring out how to clean up his workshop. Haha! Join me, one of the greatest narrators in the history of narration, next time on more Max Historica. Let's recap. Sarah and I have maxed out our simple geodesic dome, but now it's time to make it even more maxed out. We need to increase how complex our structure is.
So right over here, we actually have a dome that's just made out of triangles.
Ooh, look it, it's nothing but there's a triangle there, there's a triangle there, triangle there, triangle. So all triangles.
All triangles. And see how much bigger it is even compared to our first one?
Yeah.
And that's just by adding more points. Over here, we have one that uses pentagons and triangles.
Ooh, let me see. Okay, so we got, oh, there's a pentagon there.
Yep.
There's a pentagon there. And then we got triangles here.
Yep.
Can we go bigger than this? Because this is good, but this is still not, this is not maxed out enough. Sarah had the idea of lengthening the poles. Shish kebab skewers, I love those. I use those all the time in my science experiments. And making a bunch of pieces that fit together. So we just make a whole bunch more of these.
Yep.
And then we'll make some sort of big dome. This is awesome! So we maxed it out, and it worked great. But gumdrops started to become a little hard to work with. Every time I do one attachment, another one comes apart. So I had to get inside to hold it up with my head.
I think I've got an idea.
Oh, yeah?
Be right back. Yeah.
Okay, but should I get out or should I? It's okay, I can stay in. I could just keep fixing while it. It's collapsing a bit, but it's okay. Wait, this is inside. No, this is outside. Wait, hold on. Help, Sarah?
Hey, oh, my.
It kind of collapsed a little bit. Gumdrops, they just don't have the strength.
Exactly. I was thinking we could use something a little more sturdy, maybe like some cardboard.
Oh, yeah, and it doesn't move at all. We can totally make this. We'll max this out. I'll just put this over here. Okay, fair
right.
enough. Okay. If you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. Let's try it with books. The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is. Right now, it's pretty wide and it's not that tall, so the center of mass might be around here. But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider. The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Ah, ha, ha. Oh, careful. Now it's time to see how high, whoa, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And, ha-ha, a single stack of boxes! Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Ha-ha. Science! 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 This is a pencil. You probably have one of these at home and use it for all kinds of interesting things like writing and drawing, and that may be it. But if you have a lot of pencils, you can build stuff. I'll show you some of my favorite pencil builds. Check this out. It's a pencil cube. If you want to try building one yourself, you build it like this. Get a piece of foam and then lay out 11 pencils this way, and then another 11 that way, so they make a nice square. Then take sharpened pencils and stick them into the foam in all the gaps. Go all the way around, and then keep adding more layers of pencils, and eventually you will have a cube. Now, if you don't have 366 pencils at home, you can do the same thing with toothpicks. Now, if you want to research this on your own to find the instructions, just try looking up pencil cube. Okay, that's not the only thing we can build with pencils. Check this out, a pencil asterisk. Phil, can you max it out and add some more pencils? Yeah, so I did. I maxed it out with even more pencils. And then I thought, well, could I max it out again? So I did. This is what it looks like with even more pencils. And in fact, I removed the inside pencils and the whole thing still stays together. And then of course, this is the maximum number of pencils you can do with this configuration, because as you can see, it starts to become a sphere and you kind of run out of pencil length. There you go, maxed out pencil structures. Of course, I've used all of my pencils, but that's okay, I will buy some more. I will just write myself a note to buy more. Actually, there are sharpened pencils on the bottom of my pencil cube, so I'll just write this note with the pencil cube. What could possibly go wrong? Okay, ready? 1, 2, 3. And it's still standing! Oh, that one's not sharpened. Oh, here we go. Where'd my book go? Ooh, look at Sarah and I have maxed out a geodesic dome out of gumdrops, oranges, watermelons, and more gumdrops. But now we're making one using glue and cardboard circles. Are those the same distance? After a bunch of time assembling and gluing, we have a giant maxed out dome. Okay, there, are we done?
I think so.
We're done!
Yeah.
Yeah! Max out dome. How many points do we have?
So many.
Do you think we can lift it?
I think
I think
so,
that's the
yeah.
top. Try it.
See.
Okay, whoa. Whoa! Wait, we can spin it! It was really light and also really strong. Strong enough to hold upside down. As a fruit bowl, it'd be pretty good. This is so strong. I'm surprised at how strong this structure is. There you go, Science Max, experiments at large, geodesic dome. And now it's sort of a geodesic disco ball. I like it. Whoa, 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 okay, careful. Careful, careful. All right, putting it down, putting it down.